Today we're going to look at a paper called Activation of Intrarenal Endothelin Type B Receptor and how it improves kidney oxygenation in type 1 diabetic rats. This study was performed by Franzen et al. Type 1 diabetes, also known as juvenile onset diabetes, is caused by the fact that an individual cannot produce insulin. This is also known as insulinopenia. Insulinopenia occurs because there is damage to the pancreatic islet, specifically to the beta cells. This is often caused by an autoimmune disorder in which the patient's own immune system attacks the beta cells so that they cannot produce insulin. Since insulin is not produced, glucose is not taken up throughout the blood systemically. This can lead to various diseases downstream, including chronic kidney disease. Specifically, this can result in diabetic nephropathy. The main functional unit of the kidney is known as the nephron. The nephron works to filter, reabsorb, secrete, and excrete solutes from between the blood and the urine in order to maintain blood-solute homeostasis. Solute homeostasis can be controlled by various factors, such as renal hemodynamics, glomerular filtration rates, and tubular sodium handling. Renal hemodynamics refers to the ability of afferent and efferent arterioles to constrict or dilate, which results in different blood pressure buildups within the glomerular capillaries. Glomerular filtration rates refers to the ability of solutes in the blood to filter into the Bowman's capsule as well as the proximal tubule of the nephron. These filtration rates can be controlled by the solute concentration in the blood as well as in the nephron, as well as the pressure caused by renal hemodynamics. Tubular sodium handling refers to the ability of reabsorption and secretion to happen between the loop of Henle as well as the capillaries within the nephron. This is important for maintaining sodium concentrations within the blood as well as within the urine. Previously, these researchers performed a study in which they blocked the ETA receptor, resulting in decreased renal hypoxia in diabetic rats. This was because blockage of the ETA receptor resulted in improved intrarenal oxygen tension, also known as PO2, increased oxygen delivery, DO2, and increased renal blood flow. This makes sense because blocking ETA receptors helps to inhibit vasoconstriction as well as tubular constriction so that more solutes and nutrients can make their way to the nephron. In the current study, these researchers want to see if activation of the ETB receptor also decreased renal hypoxia in diabetic rats. This would make sense because activating ETB receptor results in vasodilation as well as tubular dilation so that more nutrients, including oxygen, could make its way to the nephron. So in this study, they wanted to see if activation of ETB receptors increased the intrarenal oxygen tension, oxygen delivery, and renal blood flow within the kidney. In order to perform this experiment, researchers induced diabetes in rats with streptozotocin, a chemical known to damage the beta cells within the pancreatic islet and induce diabetes. Researchers then injected 0.78 picomoles per hour of surfatoxin S6C directly into the left kidney. Surfatoxin S6C is an ETB receptor agonist, meaning that when this molecule binds to the ETB receptor, it will stimulate a signaling cascade similar to when endothelin 1 binds, inducing ETB receptor activation. Blood oxygen measurements were then taken in various ways. Oxygen tension was measured with microelectrodes in the renal and medulla cortex. Oxygen delivery was measured with a localized laser Doppler, and oxygen consumption was measured with an oxygen consumption statistical analysis test. Results from these rats were compared with non-diabetic control rats. The first figure looks at the oxygen tension within the renal medulla as well as within the renal cortex. Oxygen tension was measured in millimeters of mercury. Control group rats are shown by the white bars, while diabetic rats are shown by the black bars. Baseline refers to no further treatment, whereas ETB receptor agonist refers to treatment by the S6C, which acts like ET1 when binding to the ETB receptor. In both the cortex as well as the medulla, we can see that baseline diabetics have much lower oxygen tension compared to controls. This means that diabetes decreases the oxygen tension in renal cortex and medulla, which leads to hypoxia. When ETB receptor agonist was added, the oxygen tension was normalized in the diabetic rats, inferring that treatment with ETB receptor agonist can in fact reconstitute oxygen tension within these rats. The second figure that we're going to look at looks at medullary renal blood flow. This was detected in laser units through the laser Doppler. When comparing the control and diabetic baseline rats, we don't really see too much of a difference between the renal blood flow. When ETB receptor agonist was added to the control, there was a slight increase in blood flow. But when the ETB receptor agonist was added to the diabetic rat, we see a much higher increase in renal blood flow to the area. This is what the researchers had initially expected, because ETB receptor agonists should in theory cause vasodilation, which would increase the renal blood flow to the area. Activation increases renal blood flow as well as delivery of oxygen to the medulla and cortex. Increases in renal blood flow and delivery of oxygen reduced hypoxia in the diabetic rats. This is what the researchers had initially expected, because an increase in renal blood flow as well as delivery of oxygen should decrease the oxygen deficit within the renal tissue. Another thing to note that the researchers found was that reduction in hypoxia did not seem to have an effect on oxygen consumption within the diabetic rats. This is important to consider because hypoxia is often related to higher rates of oxygen consumption. The results from this study can also be compared to their previous study in which they blocked ETA receptors. In this study, they showed that ETB receptor activation had similar results to the blockade of ETA receptors in their previous study. This means that controlling vasoconstriction and vasodilation seemed to have a strong effect on controlling hypoxia within the diabetic rats. My first question is, why might hypoxia be associated with increased oxygen consumption? The second question is, how could we potentially treat renal hypoxia in diabetic patients? Think about the interplay between ETA receptors as well as ETB receptors that these researchers have discovered.